Hey there, welcome to another deep dive. It's incredible to think that we can only account for about 73%
Yeah.
of the stuff in the universe.
Yeah.
The rest, it's this mysterious dark matter.
Right.
We can't see it or directly detect it.
Right.
But what if I told you there might be a way to explain this
Okay.
using something even more mind-boggling,
Okay.
extra dimensions?
It's a concept that's been around in theoretical physics for a while now,
Right.
and some models even suggest we might be able to find evidence of these extra dimensions through experiments.
So you've given us a bunch of articles and research papers on this, and we're going to try to break down the most fascinating and important parts for you today.
Sounds good.
One of the things that really jumped out at me was this Randall-Sundrum model,
Okay.
or RS model.
Yeah.
It uses something called warp geometry to try and solve a big puzzle in physics, the hierarchy problem.
So the hierarchy problem essentially asks, why is gravity so much weaker than the other fundamental forces? The RS model proposes that our 4D world, what physicists call a brane,
Okay.
actually exists within a higher dimensional space.
Okay.
And this space has a warped shape, kind of like a mountain range.
Okay, so I'm picturing our universe as like a sheet
Yeah.
draped over a bumpy landscape. Does that work?
That's a good way to visualize it.
Okay.
And because of this warping, gravity might be more concentrated in certain regions of this higher dimensional space.
Mm.
Imagine one side of that mountain range being much steeper than the other.
Okay.
Gravity might be much stronger on the steeper side because it's more concentrated there.
So in the RS model, our 4D brain is in a spot where gravity is weaker, and that's why it seems so much weaker
Exactly.
than the other forces.
The warping of space-time in this higher dimensional space could create a sort of gradient in the strength of gravity, making it weaker in our particular slice of the cosmos.
Now, how does dark matter fit into all of this?
Well, some theories propose that what we perceive as dark matter could actually be the result of a specific particle interacting with a fifth dimension. This particle, a type of fermion, could act as a sort of portal.
Okay, so like a doorway.
Not necessarily a doorway that something could travel through,
Okay.
but more like a bridge allowing for interactions between these dimensions.
Okay.
The idea is that this fermion extends into this extra dimension,
Okay.
and its interactions there create gravitational effects that we're interpreting as the presence of dark matter.
So we can't see the fermion directly,
Right.
but we see its footprint in the form of gravity.
Precisely.
Hmm.
And while we don't have the ability to directly detect such a particle,
Right.
yet future experiments, like those at the Large Hadron Collider or using gravitational wave detectors, could potentially provide evidence of its existence.
So it's not just a theoretical possibility, we might actually be able to find proof.
Yeah.
That brings us to the question of experimental evidence. What are some of the ways physicists are trying to test these theories of extra dimensions?
One of the key predictions of theories with extra dimensions is the existence of something called Kaluza-Klein modes,
Okay.
often shortened to KK modes.
Right.
Essentially, these are heavier versions of the graviton,
Oh,
the particle responsible for gravity.
so like gravitons with extra baggage. How would we even detect something like that?
One way is through missing energy signatures.
Okay.
At particle colliders, like the Large Hadron Collider
Right.
or LHC,
All right.
imagine two particles colliding at extremely high speeds.
Okay.
If extra dimensions exist, some of the energy from that collision could leak into those dimensions,
Okay.
appearing as missing energy.
So like a tiny bit of the energy just vanishes.
Exactly.
Wow.
And that's what physicists are looking for, these discrepancies in energy that can't be accounted for by our current understanding
Right.
of particle physics.
Now, I understand that the RS model, with its warped geometry, has some specific predictions about these KK modes.
Right.
What makes them different from the KK modes predicted by other theories?
In the RS model, because of that warped space-time,
Okay.
the KK modes are predicted to be much heavier
Okay.
and more strongly coupled to our 4D world.
Go ahead.
This means they would be more likely to leave detectable traces in high-energy collisions.
So instead of just seeing missing energy,
Right.
it's about seeing these heavier particles popping up as well.
Yes.
Right.
These heavier KK modes would create what we call resonances in the collision data. Imagine tuning a radio and hitting a specific frequency where you get a strong signal.
Right.
That's analogous to what we might see at the LHC if the RS model is correct.
So the existence and properties of these KK modes could tell us a lot about the nature of extra dimensions.
Mm,
Not just whether they exist,
right.
but what they might be like.
Exactly. It's a fascinating area of research
Yeah.
because it has the potential to completely revolutionize our understanding of the universe.
This is definitely a lot to wrap our heads around.
It is.
But it's this kind of exploration that pushes the boundaries of science and leads to incredible discoveries.
It's amazing to consider how these different theories offer distinct perspectives on the nature of extra dimensions.
Mm.
We've got models where gravity is weakened because
Right.
it spreads out in these large extra dimensions. And then we have the RS model where
Right.
warp geometry leads to gravity being concentrated in specific areas.
Kind of like the difference between a flat plane where everything spreads out evenly and a mountain range
Exactly.
where things are clustered in peaks and valleys.
And these different landscapes, so to speak, result in unique predictions that we can look for in experiments.
Hmm.
It's why the work being done at places like the LHC is so crucial. It could tell us
Right.
which of these landscapes is the most accurate representation of reality.
Now, going back to that fermion particle acting as a portal to another dimension, I'm still trying to wrap my head around that.
Yeah.
Is it like something could travel through this portal?
It's not so much about traveling between dimensions like you might see in science fiction.
Right.
Think of it more as a connection that allows this fermion to interact with something in that extra dimension.
Okay.
Remember, our 4D brain is embedded within this higher dimensional space, and this fermion is essentially sticking out
Okay.
into that space, interacting with whatever might be there.
So it's got 1 foot in our world and 1 foot in this other dimension.
That's a great analogy.
Okay.
And it's those interactions in that extra dimension that are thought to create the gravitational effects
Okay.
we observe as dark matter. It's like the fermion is tugging on our brain from the other side, but we can only see the tugging, not the fermion itself.
It's wild to think that we might be able to detect those subtle tugs through things like missing energy
Right.
at the LHC or even through gravitational waves.
It is, but you're right. These are incredibly subtle effects, and the experiments are complex.
Right.
Distinguishing these signals from background noise is one of the biggest challenges.
Okay, but let's say we do find concrete evidence of extra dimensions. What then?
Yeah.
Does it change everything we thought we knew about the universe?
It would definitely be a paradigm shift.
Yeah.
It would mean that our current models of physics are incomplete and that there's a whole other layer of reality out there waiting to be explored.
It's like finding a hidden room in your house that you never knew existed.
I like that. And who knows what we might find in that hidden room.
Right.
It could revolutionize our understanding of everything from gravity to the fundamental forces to the very nature of reality itself.
So potentially this could even be bigger than Einstein's theory of relativity.
It's difficult to say for sure, but the implications are definitely massive.
Yeah.
Just imagine if extra dimensions exist, there could be other universes out there,
Wow.
maybe even with different laws of physics.
Now we're talking about parallel universes and alternate realities. That definitely sounds like science fiction,
Right.
but it could all be possible if these theories pan out.
If we connect this to the bigger picture, the existence of extra dimensions could completely change our understanding
Right.
of the cosmos, its origins, its evolution, and its ultimate fate.
Yeah.
It could even lead to new technologies and scientific breakthroughs that we haven't even conceived of yet.
It sounds like we'll have enough material for deep dives for years to come.
Absolutely. And this is an active area of research. So new theories and models are always being developed,
Right.
and the data from experiments is constantly being analyzed and refined.
You mentioned earlier that the LHC might be able to detect extra dimensions through missing energy and those KK modes.
Right.
Can you explain that in a bit more detail?
Sure, the LHC is essentially smashing protons together at incredible speeds.
Okay.
If extra dimensions exist, some of the energy from these collisions
Right.
could escape into those dimensions, effectively vanishing from our perspective.
So it's like a tiny bit of the energy just disappears without a trace.
Exactly.
Yeah.
And that's what physicists are searching for. The events where the total energy after a collision is less than the total energy before.
Right.
This missing energy could be a sign that it's leaked into extra dimensions.
So it's like a cosmic accounting error.
In a way, yes. Now, those Kaluza-Klein modes,
Right.
the heavier versions of the graviton also come into play here.
Right. Those are the ones that are more noticeable in the RS model because they have more oomph.
Exactly.
So how do we detect those?
They would show up as resonances or peaks in the energy distribution of the particles produced in the collisions. Essentially, these KK modes have specific masses
Right.
And when the energy of the collision matches those masses,
Sure.
we'd see a surge in the data.
So it's like tuning a radio and finding a station at a specific frequency where the signal is strongest.
A perfect analogy.
Okay.
And by analyzing the characteristics of these resonances, their strength, their energy,
Huh?
we can infer information about the nature of the extra dimensions.
So we're not just looking for the existence of extra dimensions, we're trying to understand their properties,
Right.
their shape.
It's their size. It's like trying to map out a hidden landscape based on the shadows it casts.
That sounds like detective work on a cosmic scale.
Precisely.
Yeah.
It requires a combination of theoretical ingenuity, experimental precision, and a lot of imagination.
Speaking of things that require imagination, one of the articles we gave you mentioned the hierarchy problem.
Right.
Can you remind us what that is?
The hierarchy problem refers to the huge difference in strength between gravity and the other fundamental forces,
Okay.
like electromagnetism and the strong and weak nuclear forces.
Right.
It's a puzzle that's been baffling physicists for decades.
So gravity is like the weakling of the forces.
Well, it depends on how you look at it. On large scales, like the scale of planets and stars, gravity dominates, but at the subatomic level, it's incredibly weak compared to the other forces.
Okay, so how do extra dimensions help explain this enormous difference in strength?
One explanation proposed by the RS model is that gravity's strength is diluted because it's spreading out into these extra dimensions. Think of a sheet of paper.
Okay.
If you draw a dot on it, the dot is confined to the 2 dimensions of the paper.
Okay.
But if you could extend that dot into a 3rd dimension, it would become a line spreading out its ink.
So gravity is like the ink spreading out into these extra dimensions and becoming weaker in our 4D world.
Exactly. And in the RS model, the warping of space-time could further concentrate gravity in certain regions, explaining why it's so much weaker on our brain.
So these extra dimensions aren't just some abstract mathematical concept. They can have real measurable effects
Absolutely.
in physics we observe.
And the fact that we haven't directly detected these extra dimensions yet
Right.
might just mean that they're curled up or compactified at a scale
Okay.
too small for our current experiments to probe.
It's like trying to see a tiny ant on a football field from a distance. It just looks like a dot.
A great analogy, but with more powerful tools like
sure.
the LHC or future gravitational wave detectors, we might be able to zoom in and see that ant, revealing the detailed structure of these extra dimensions.
This has been an incredible deep dive into the mind-bending world of extra dimensions. We've explored how these extra dimensions and warped geometry could potentially solve some of the biggest mysteries in physics,
Yeah.
like the hierarchy problem and the enigma of dark matter. And we've seen how these theories lead to testable predictions
Right.
that are being actively investigated in experiments around the world.
It's really a testament to the power of human curiosity and our drive to understand the universe around us. Who knows what incredible discoveries await us
Right.
as we continue to push the boundaries of knowledge.
And on that note, we'll be wrapping up this deep dive into extra dimensions.
Yeah.
Don't forget to like, subscribe,
Yeah.
and share Deep Dive with anyone who might be interested in exploring these mind-blowing concepts.
Absolutely.
And stick around for a moment longer because, as always, we have a special ending after a short pause.
It's truly remarkable to think that we might be living in a universe with more dimensions than we can perceive.
Yeah, it's a concept that really challenges our everyday understanding of reality. We're so used to thinking in terms of 3 spatial dimensions and 1 dimension of time.
And these extra dimensions, if they exist, might be curled up or compactified at such a small scale that we simply can't experience them directly with our senses.
So kind of like a garden hose that from a distance looks like a one-dimensional line.
Yeah.
But up close, you can see it has a whole other dimension
Exactly.
curled up in a circle.
That's an excellent analogy.
Yeah.
And just as we need a microscope to see the details of that curled up dimension, in the hose, we might need much more powerful tools to probe the fine structure of these extra dimensions in our universe.
And those tools are things like the LHC and future gravitational wave detectors.
Exactly. These experiments are constantly pushing the boundaries of what we can observe.
Right.
And it's possible that with more sensitive instruments, we'll be able to uncover evidence of these hidden dimensions.
Now, we've talked a lot about the RS model and its warped geometry.
Right.
But are there other models that physicists are exploring to explain extra dimensions?
There are. The RS model is just one of many theories that propose the existence of extra dimensions. Some models suggest these extra dimensions might be large, meaning not necessarily curled up at the tiny Planck scale, but potentially much larger,
Mm.
even macroscopic.
Macroscopic extra dimensions. So are you saying there could be a whole other universe
Yeah.
right next to ours, just separated by a dimension we can't see?
It's a fascinating idea, and some theories do explore that possibility.
Wow.
However, these large extra dimension models have their own set of
Right.
challenges and predictions, and experimental evidence is still lacking.
So it's like there's this whole landscape of possible theories,
Right.
each with its own unique set of features and predictions.
Precisely. And it's the job of physicists to explore this theoretical landscape,
Right.
develop testable hypotheses, and see which models best match the experimental data we gather.
It sounds like the search for extra dimensions is really a journey into the unknown,
It is.
pushing the limits of both our theoretical understanding
Right.
and our experimental capabilities.
And it's this constant interplay between theory and experiment
Yeah.
that drives scientific progress and leads to profound discoveries.
Well, I think we've given our listeners a lot to ponder today.
I hope so.
We've gone deep into the mind-bending realm of extra dimensions, exploring how they might explain
Right.
some of the biggest mysteries in physics, like the hierarchy problem and the nature of dark matter.
We've also seen how these theories offer tantalizing hints of what might lie beyond
Right.
our familiar four-dimensional world, opening up possibilities for new physics, new universes, and a deeper understanding of the cosmos.
It's a reminder that there's still so much we don't know about the universe, and that the quest to unravel its secrets is an ongoing adventure.
Absolutely.
And as always, we encourage you to continue exploring these fascinating topics on your own.
There's a wealth of information out there, and new discoveries are being made all the time.
And that wraps up this deep dive episode. We hope you found it insightful and thought-provoking. Don't forget to like and subscribe to the show so you don't miss out on future deep dives into the most fascinating corners of science and knowledge.